Okay, well, I just got the chime on my computer. It says it's 12 o'clock. We're ready to roll. Welcome back to class. I thought what I'd do is I'd start off quickly by talking about what I'm thinking with regard to the final exam. Because again, I know we have class on Monday, class on Tuesday, and then the final exam on Wednesday. Doesn't really give you a lot of prep time, and some of you are probably going to want to start reviewing notes this weekend. So let me jot down some things here for you that I've been thinking of, and happy to hear your input on any of this as well. So because this is a cumulative course in nature, all of the material that we've used at the beginning, we're still using here at the end. We're using KVL, we're using KCL, we're using Ohm's law, we're using superposition, Thevenin equivalence, Norton equivalence, all of that. It's going to be that all of that material is still important. You still need to know it, but the focus will be more on some of the topics that we've covered recently. So I just jotted these down over the last 10 minutes prior to class starting up, and these are in no particular order. So this isn't from most important to least important, but these are topics that I think are fairly important, and somewhere it's probably going to be the types of topics that are going to play a role in us for our final exam. So let's jot those down. I lost my date here somewhere. I have no idea where my date went to. There you are, right there. Okay, so this is what I believe are the topics that are pretty important for us that we should be focusing on. Number one, phasors, sinusoidal steady state. Number two, with the second order differential equations, just in general, we looked at second order differential equations. So we did all of this. This is in the time domain, right? This is in the time domain here. And then we looked at their solutions. And the solutions boiled down to find the characteristic equation, find the natural frequencies, find the homogeneous response, C, homogeneous response, find the forced response, then find the complete response, and part of that was using initial conditions as well. If no initial conditions are given, then the complete response has, for a second order differential equation, has two unknown constants in it. So we spend a good amount of time on that. We transitioned in, once we looked at that, we transitioned into and said, all right, let's develop and let's get the differential equation from the circuit. So developing the second order differential equation. From the circuit. These can be, I don't want to say hard, they can be a little challenging because sometimes the process doesn't look like substitutions are going to go the way they would seem. Sometimes the substitution is a little odd, a little bit different. So then we started to work our way out of that world. We focused more on sinusoidal steady state. Then we went into the Laplace transform world, and we talked about Laplace transforms. With Laplace transforms, we have properties, functions. So when I say functions, when I say this, I'm implying, for example, 3 delta of t Laplace transforms into what function? Into, we know the Laplace transform of delta of t is 1, so that just transforms into 3 times 1, which is equal to 3. So the functions, we should know certain functions. They're in our tables. We have tables. We should be able to find those pretty quickly. And then there are properties, and we should know how to use properties to develop or work through Laplace transforms to get them easier versus going through the integral. There was always the integral. So there was the definition of the Laplace transform. Some of us really don't have the calc background to get here. So for that reason, I don't want us to have to figure out the Laplace transform based on the integral. So here it was a one-sided Laplace transform. It was 0 to infinity of f of t e to the minus st dt. So don't focus solely on this. Focus more on the properties and what the properties are, given that we know some functions already. That's the way to work with those Laplace transforms. Obviously, once we had the Laplace transforms and we knew that they were going to be appearing as rational functions, we did partial fraction expansion. And in partial fraction expansion, we had three different cases. We had real distinct roots, real repeated roots, complex conjugate roots. So we had all of that in the partial fraction expansion. So we were looking at that. Buried in all of this and in the sinusoidal steady state, we had mutual inductance. Don't forget that. We haven't done anything on an exam with mutual inductance yet. We didn't have that on our first exam. So mutual inductance. An extension of mutual inductance was the ideal transformer. So we looked at the linear transformer and the ideal transformer. I would focus on the ideal transformer, not the linear transformer. Most of what we do is the ideal transformer. Just the other day, we were talking about the system function. We'll talk just a bit about that today. So that system function was h of s. In fact, the relationship was the output, whatever the output is. So usually y is the output, x is the input. Y of s equals h of s times x of s. So we have that relationship. You can goof around with that relationship. You can solve for x of s. You can solve for y of s. You can solve for h of s. So we could do an example of that. I think I might start off with an example of that today. This we'll see almost immediately today as well, the convolution integral, which is a very powerful and important concept. Obviously, we spent time with complex numbers. I'm thinking of giving you some easier problems and then some that are a little more challenging. So for example, I think a complex number problem would be pretty easy. It's just mathematics. You don't have to do any circuit analysis, but you have to know your complex numbers. I think I could do some things with regard to Laplace transforms that don't have to do with circuit analysis as well, or some partial fraction expansion. That's just mathematics. So we dealt with complex numbers, we dealt with singularity functions, and building other functions with singularity functions. And obviously built into all of this, somewhere in here, there was impedance and admittance. Superposition, because now sometimes superposition must be used in certain cases. We had certain cases where superposition had to be used. And then you can go into your mesh and your nodal analysis and your Laplace transforms of those, and et cetera, et cetera, et cetera. They're all sort of tied together. So I think those are the basic topics that we've covered that will be emphasized on the final exam. Questions or comments about any of those? Don't know what I mean by any of them, or any questions at all? Okay, hearing none, we'll just continue with our work. So we finished the last time, we were looking at the relationship between the system function and the input and the output. So just as a reminder, if y of s is an output and x of s is an input, then h of s is defined to be equal to the output over the input, y of s over x of s. Now, I've got to tell you very clearly, I'm going to write it down now. This is a big mistake that students make over here. So I'm going to put it in this box. We finished with H of t last time. Somebody remind me what H of t is called.
Homogeneous response.
Okay, it has the same form as the homogeneous response. That is correct. But what do we call H of t? There's a very particular name to it.
The transfer function.
H of s is the transfer function. H of t is?
Impulse response.
Excellent, excellent. It is the impulse response. And that impulse response it is a scaled version of the homogeneous response. So a lot of students write this. They see this, and they want everything in the time domain to be the same as everything in the frequency domain, but it is not. And so they write this. And that couldn't be any more wrong than you can imagine. H of t is not y of t over x of t. In fact, we're going to show you what it is today. We're going to show you the relationship between y of t, h of t, and x of t. So let's stay in the frequency domain for a moment, and let's just pretend, let's let x of t be equal to 3 u of t plus 2 delta of t. We'll make it easy. So let's just pretend that that is the input function. And let's pretend I know I've measured the output. And the output, I could make it anything, but let's make it 10 e to the minus 6t, e to the minus 6t. Here's the question. What is h of t? So we can't use that because that doesn't work. So here's what we have to do. In order to find h of t, we have to find h of s. Once we have h of s, we do an inverse Laplace transform, and we can find h of t. So let's calculate h of s by computing x of s. So x of s is equal to 3 over s plus 2. Let's write that as 3 over s plus 2s over s, which is equal to 2s plus 3 divided by s. Y of s is equal to 10 over s plus 6. Perfect. Now what do we know? We know that h of s is equal to y of s divided by x of s, output over input. And so that's equal to output 10 over s plus 6 divided by 2s plus 3 over s. That's equal to 10 over s plus 6 times s divided by 2s plus 3. Not the coolest numbers, but that's all right. 10s over s plus 6. And then I'm going to do this, I'm going to factor the 2 out, and then s plus 3 halves. So one more, h of s is equal to 5s over s plus 6, s plus 3 halves. Now, let's do our work. That's a over s plus 6 plus b over s plus 3 halves. We can find a and b, so let's go ahead and do that. A equals s plus 6 times h of s, evaluated when s equals minus 6. So that's equal to 5s divided by s plus 3 halves, evaluated when s is equal to minus 6. Let's put in a minus 6. Minus 6 times 5 here in the numerator, minus 6 plus 3 halves. So minus 6 is minus 12. So minus 6 times this 5 is minus 30 in the numerator. In the denominator, this is minus 12. Minus 12 halves plus 3 halves is minus 9 halves. Just do a little flip there. So this is equal to 30 times 2 divided by 9. The negatives cancel each other out. Cancel, cancel. Equals 60 over 9. Great, that's A. Let's find B. B is equal to S plus 3 halves times H of S, evaluated when S is equal to minus 3 halves. And that's going to be equal to 5S over S plus 6, evaluated when S is equal to negative 3 halves. Now I'll just plug and chug. 5 times minus 3 halves divided by minus 3 halves plus 6. Again, keeping in mind that 6 is 12 halves. So in the denominator, we have minus 3 halves plus 12 halves. This time it's a plus 9 halves. And in the numerator, we have minus 15 halves. The cancellation of the 2's, I can pull a 3 out of there in the numerator. And if I do, that will give me negative 5. So that's equal to negative 5. Pull a 3 out of the denominator, minus 5/3. Great. Therefore, H of t equals, well, let's see. Just looking at my numbers, I have 60/9. That's A. So 60/9 e to the minus 6t minus 5/3 e to the minus 3 halves t. And again, in our book, our author likes to put a u of t on these for a reason. The reason is because we're using the one-sided Laplace transform, so we don't care about what's going on the other side, so we just pop a u of t in there. And there's our answer. So we can use this system function in a variety of different ways to find the impulse response. We could give you any two of these that we started with, any two. Here I gave X and I gave Y, but I could have given H and Y, and then you could find X. I could give X and H and you can find Y. You could do this in any manner that you want to. It's a real nice, simple mathematical formula to use. Okay, so we said earlier, H of t is not equal to, it's not equal to, whoops, not equal to, I'm stepping ahead of myself, is not equal to y of t divided by x of t. It is not equal to that. Okay, so what is it equal to? That's the question. What is it equal to? So I'm going to write this here, just so you know, and then we're going to come back to it. So what we're going to have is that y of t, the output, is equal to x of t, the input, convolved with h of t. It is not a times. This is convolution. Convolved with h of t. So y of t is x of t convolved with h of t. Notice in here, right now, we don't even know how to find it. In other words, it's not written separately like it is over here. It's buried in this convolution, and we don't even know what the convolution is. So let's talk about convolution and what convolution is. Now, because the convolution integral is going to be new to you, from time to time, you're going to make a mistake in the terminology. And so you're going to say, like, for example, here, notice what I wrote. X of t is convolved with h of t. A lot of people in their terminology say it's convoluted with. So there's nothing convoluted about this. It's convolved with is the correct terminology. So I want you to consider the following here. So the definition of convolution is the following. So let's let C of t, C stands for convolution, we're going to let this be equal to f of t convolved with g of t. And I want you to see that we're going to define this. This is defined to be the integral from minus infinity to infinity of f of tau g of t minus tau d tau. I'm going to write this here with no proof. So this is also equal to minus infinity to infinity of g of tau times f of t minus tau d tau. Let's write it down. It's just an equation, which really means the following. This really means that c of t is equal to f of t convolved with g of t, which is equal to g of t convolved with f of t. It's like addition. Doesn't matter which order you add, or it's like multiplication. It doesn't matter which order you multiply. A times B is equal to B times A. It doesn't matter which way you convolve. Now, there's a lot that we can say about this. And so I wanna make mention of a couple of things. First, the output of this integral is a function of time. See, it's a function of time. Function of time, function of time. And in the integral, we have tau as our dummy variable that we integrate away. So I want you to see what f of t times g of t minus tau is. So what we do here with these functions is they start in the time domain. I'm going to make these up. So let's just pretend the function looks like the following. For now, I'm going to make all of that 0. So there's nothing there, okay? And that way we can change our integral and our lower limit here for this one side of Laplace transform. We'll come back and we'll change that lower limit to 0, even though some people like to put 0 minus. So don't worry about what's over here. For f of t, let's just pretend it looks like this function. There it is. I know that's wonderful and at the same time kind of meaningless to you. So this is a t-axis. So here's the first question. My first question is, well, what is f of tau? The answer is, all I'm doing is I'm changing the name of the axis, and the function looks identical. Now, I'm going to have a hard time drawing this to be identical, but it looks identical. It's the exact same function. So when we do this convolution integral, we take this function in the time domain, and we just change it to be a function of tau. Why do we do that? We do that so that we can integrate away the tau and then get a function left that is a function of time, which is what we want when we do our convolution integral. So that is what f of tau is. So side by side with that, I have a g of tau. I'll make this one easier. So we'll start with g of t, t-axis. And maybe g of t looks like this, for example. Okay, just so we can identify what it looks like. That's g of t. All right, well, what is g of tau? Looks exactly the same, except the axis is changed to a tau axis. And it looks exactly the same. So it goes up to here, and then comes down and does that. Then, this is the real question. I want to get to what is g of t minus tau? Well, let's start this in steps. I have g of tau. Let's go to g of minus tau. I know you all know what happens with g of minus tau. It just flips along the y-axis. So it is this function flipped over to this side. So I still have this tau axis. It gets flipped over, and so now it looks like this. I can draw this correctly. It looks like this, and then that. Okay? So it's flipped over. So that's there. One more step. Now I change the inside to g of t minus tau. And so g of t minus tau looks like the following. And I'm going to draw it for any t. Still on the tau axis. G of t minus tau is just shifted somewhere. It could be shifted anywhere. So I'm going to draw a number of different g of t minus taus. So that's 1, Here's another one. There's one there. Here's another one. Let's continue out here. Okay, here's what's important. This leading edge, the leading edge of this is going to be, so we go back to this picture where it's not shifted. And I look at what are the tau values, on these edges, these important points. So right here, obviously that's 0, and I'm going to make this up. Let's just pretend this is 5, which would mean that was 5. Okay, so when I look at these edges here, and I want to know where they are, it depends on the value of t. Okay, it depends upon the value of t. But once we know that value, we're going to use that value of t plus these values to find out what this is. So for example, if I told you t was equal to -10, then g of -10 minus tau has this function right here. It'll be this one, and this will be -10, and this one here will be -15. If I said t was equal to, making it up, let's call it 20, then this leading edge here is 20, and this edge right here is 20, and I'm sure I didn't draw this well, but it would be 20, and then look at this distance from here to here was 5, so it'd be 20 minus 5, which is going to be 15. And I know it doesn't look like it's 15 on this graph. Don't worry about that. So basically, when we talk about what's taking place, here's what's going on. And then I'm going to try to explain to you pictorially why we have what's going on. So I'm going to look at both of these at the same time. So these two functions, I want you to think of, this is your system function, h of t. It's just going to, so we can see it, let's just pretend h of t looks like this. So what does this mean? This means if I put an input into the system, which is an impulse, the impulse goes into the system, and this is what will come out. This will be the output if I put an impulse in. But if I put anything else into the system that's not an impulse, so I'm going to give you an input here. And so let's make this one easier to understand. So this, then let's make it go straight down like that. So that's the input. Let's just pretend, for argument's sake, I'm going to give you some numbers, 10, 20. This looks like it's about 5, and this looks like it's about 15. Okay, this is going into the system. It's the input. What part of that function, what part? This part? This part? Which part of this function does the system see first? Which part of the function does the system see first? Does it see this end here, or does it see this end here first? Any thoughts on that? It sees this first right here. That's t is equal to 0. So when t is equal to 0, this starts coming into the system. Well, guess how we make a visual that shows that that goes into the system first. Watch this. This is how we make that visual. So I start sliding it in this direction as it goes into the system. You can think of this literally being broken up into a sequence of impulses whose areas are the height of this function. And this is your author shows it like this in your textbook. I'm not going to harp on that. I'm going to focus more on the function. So it sees these impulses first. And when it sees each of these impulses, because we have a linear time invariant system, when the first impulse goes in, I get an output that looks like this. When the second impulse goes in, it goes in a little bit later. So I get an output that's scaled, but comes out later. And then I'm just going to add those all together. So when we talk about this convolution integral, what we are doing is we're taking one of the two of these, either the system function or the input. It's easy to understand why it would be the input, but mathematically it's the same if it's the input or the impulse function. And so we flip it over and then we start sliding it in through the system function. That's why the convolution integral works the way it does for our circuits. Okay, having said that, let's now go back and focus on this convolution integral and watch some really cool things about the convolution integral. So first things first. So our convolution integral is, by definition, we said it's defined to be equal to the integral from minus infinity to infinity of f of tau, g of t minus tau, d tau. Okay, and I said, yeah, it could be the other one, but focus on this one. Now, here's the first thing we're going to do. Let's restrict f of t and g of t so that f of t equals 0, t less than 0, and g of t equals 0 for t less than 0. If that's the case, right here in this integral, f of tau is going to be 0 for tau less than 0. I can change the lower limit. Therefore, I can shift that up to 0. So I'm going to do that. So now we have c of t is equal to the integral from 0 to infinity f of tau, g of t minus tau, d tau. Okay, so that's our integral. Now here's what I want to do. I want to show you what this integral really is, so you'll have an understanding. So I want to take the Laplace transform of c of t. We know that that's going to be c of s. And it's equal to, remember the definition of the Laplace transform. So it's the integral from what to what? You better remember, definition of the Laplace transform. I wrote it right at the very beginning of the class today when we were going through things to prepare for the exam.
F of t e to the minus st dt.
Good. So here we go. T equals 0. I want you, because I'm going to have two integrals here, I want you to specifically know t equals 0 to infinity, and then it's going to be, in this case, c of t e to the minus st dt. Okay. Now I'm going to substitute this in for c. So this is equal to the integral t equals 0 to infinity of the integral, so we're going to be really careful here so that we know, tau equals 0 to infinity, f of tau, g of t minus tau, d tau, all times e to the minus st dt. So I don't know how familiar you are with integrals and when we can change the order of integration or not. An integral is a summation. So changing the order of the summations is allowed in this case. And so what I'm going to do is I'm going to change the order of summation. So I'm going to do that. All right, so let me write the notes so you know what I'm doing. So we're going to just reverse the order. Of integration. Of summations. Just remember, an integral is a sum. We're adding it up. So I'm going to reverse the order. So therefore, C of S is going to be equal to the integral from tau equals 0 to infinity. So, and then I'm going to leave all the rest of this inside here. So the integral t equals 0 to infinity. And then what do I have? I still have f of tau, g of t minus tau. And then I have e to the minus st. And I've got to get the dt in here. So we have to switch the orders of dt and d tau. We have to do that. Because this dt goes with this integral on time, and this d tau goes with this integral here on tau. So I've got an inner integral. This is the inner integral. And then I have an outer integral. And this is the outer one. All right. Now, take a look at that. Take a look at the inner integral and tell me what is not a function of t in the inner integral. Not a function of t.
Yeah, for tau.
That's correct, f of tau. So I'm going to pull that out of the inner integral, but it still can't pull it out of the outer integral because the outer integral is a function of tau. It's an integral on tau. But I can pull it out of the inner integral. So I just did that. And now I'm left with the integral from 0 to infinity of g of t minus tau times e to the minus s tau. I'm sorry, e to the minus st, not s tau, dt, d tau. Does this, everything inside the brackets, look vaguely familiar? See if you agree with this. That, the whole thing with the integral, is the Laplace transform of g of t minus tau. Do you agree with that? Right, it's the integral, 0 to infinity, of anything times e to the st, e to the minus st, dt. There's the anything. That's the Laplace transform of anything. Okay, well, what's the Laplace transform of g of t minus tau? That's a time shifting property, right? So let's recall that Laplace transform is e to the minus s tau times g of s. That's what that Laplace transform is. I'm going to put it in there. E to the minus s tau times g of s all times d tau. We're almost home free. The math is beautiful. We're almost where we need to be. Now, what inside of this integral, just a reminder, this is c of s, what inside of this integral has nothing to do with tau. It can be pulled out of the integral.
The g of s.
Good. Excellent. The g of s. So I'm going to pull it out of the integral, and now I'm left with the integral tau is equal to 0 to infinity f of tau e to the minus s tau d tau. Oh my gosh, what's that integral? See if this helps. T, T, T. I can change that. It's a dummy variable. I can change it to whatever I want to. What's that integral equal to?
F of s.
Unbelievable. So here's our result. C of S is equal to G of S times F of S. Convolution in the time domain is multiplication in the frequency domain. I'm going to write that down. This is another reason we love the frequency domain. Convolution is an ugly, ugly function, but multiplication is real easy. So we love the frequency domain. Love the frequency domain. So that means the following. So we were looking at the beginning for us, we had C of t equals G of t convolved with F of t. And we know that that Laplace transforms into G of S times F of S. G of S times F of S. Okay, I told you it doesn't matter if this works. You can see now with the multiplication in the frequency domain, you can see how this is clearly equal to F of S times G of S. I think everybody sees that. So clearly that is, in this case, that's F of t convolved with G of t. So G of t convolved with F of t is equal to F of t convolved with G of t. That's what that says. So now let's consider this application that we had with our transfer function. So we wrote it this way the other day, V of S equals, keeping in mind, output, H of S, VI of S. What does that mean? Therefore, V of t equals H of t convolved with VI of t. Now, when we have nice functions, the convolution and doing the convolution mathematically is pretty straightforward. It isn't too difficult, but it can be. It can be. And so oftentimes we like to avoid the convolution integral, and we actually like to go to the frequency domain. But just to be clear, first of all, let's box a couple of things here. V of t is also equal to VI of t convolved with H of t, since they're the same thing. So just want to be sure that we write that down. It's the same thing. So what does that mean mathematically? VO of t is equal to the integral from 0 to infinity of, and then you take your pick which one you want. So I'll start with VI of tau, H of t minus tau, d tau, which is also equal to the integral 0 to infinity of H of tau, VI of t minus tau, d tau. And you can do a mathematical manipulation on either this integral or the first integral, and you can prove that both integrals are equal to each other. You can prove that. It's a simple mathematical manipulation. This is what I like. I like systems. I talked to you the other day about, I'm really kind of a systems engineer. I like a systems approach. And so the way I see this is this way, and I hope this is helpful to you. So I see the input over here. Here's my input. Let's put a dotted line there. So here's my input. Now on the top, I'm going to do this in the time domain. My input is VI of t. This is my system here. So let's label that. This is the system. And over here is going to be the output. So from the system perspective, in blue, VI of t, H of t is the system, and then my output, VO of t, equals VI of t convolved with H of t. And everything in blue is in the time domain. If you want to work in the time domain world, which we know is generally harder. If we want to work in the frequency domain, then we're down here, and we have VI of S, and we have H of S, and then we have VO of S equals VI of S times H of S. That's the picture that I see. I see that in my head all the time. That's the picture. Now, let's go and look at some examples here. Put it on there. All right, so if VI of t equals e to the minus t u of t, notice I'm popping these u of t's in here to make sure that I don't have anything on the negative side of the time axis. And h of t equals e to the minus 2t u of t. You will understand why it's important that a system function doesn't have an output for negative values of t, because it says if you put an impulse into the circuit at t is equal to 0, you will have already gotten some output out at negative values of t. What do you think? How possible is that in the world that we live in? How does the circuit know to start giving you some output? How does it know you're going to put an input in at t is equal to 0? So that's an interesting situation, and we'll talk about that in terms of causality in our linear systems course when we do our signals and systems. Okay, if this, find V0 of t using the convolution interval. So we'll start by using the convolution interval. Okay, so step one, I'm going to step this out for you. Step one, convolution integral. First of all, we need to know what is VI of tau and what is H of tau. So what's VI of tau? Anybody? VI of tau? Just replace t by tau. Don't make it hard. H of tau. E to the minus 2 tau u of tau. The only reason we have to put a tau in there is because we're doing this integration. We want our answer to be in terms of the time domain. We want the t in the time domain, so we just use this dummy variable to do our integration. That's the only reason we do that. So now we have two choices. Two choices. So regardless of which choice we use, we're going to need to know what is either this or this. So if we want the VI of t minus tau, if where there's a tau, replace it by t minus tau. So that's that. Over here, to the minus 2, t minus tau, u of t minus tau. So if we're going to use the convolution integral, we have to know what the functions are and how to be able to substitute them into the integral. From here, we have to decide which integral we want. So we know that VO of t is equal to it's either the integral from 0 to infinity of, it's either these two multiplied together. So let's write it out. VI of tau, H of t minus tau, d tau, or it's this one, and they will both give you the same exact answer. I'm not going to do both of them. So it's one or the other. I'm just going to choose the first one because it's the first one there, not because it's easier. There are times when we want to be careful and choose the one that's easier. So this is the integral 0 to infinity. So vi of tau, e to the minus tau, u of tau, h of t minus tau, e to the minus 2, t minus tau, u of t minus tau, d tau. Okay, so that's step one. Let's get that set up, right? Deciding which of those are we going to use. And now, the next step is, once we've done that, is to compute the integral. So in computing this integral, the first thing that you should see is this and this, which before this course, we weren't used to seeing those. So I want to remind you in step 2 is change the limits of integration by evaluation of any unit step functions in the integral. So there are 2 of them in the integral. I know what you know. I know that you know what step functions look like, but I'm going to draw them for you again. That's what u of tau looks like. And this is what u of t minus tau looks like. I don't know where t is. And t can be anywhere. T can be further over here, or it can be over here. All right, so let's start with the first one. This is 0 for t less than 0. Well, the lower limit is 0 already. Otherwise, it's 1 for t, I'm sorry, not t, tau. For tau greater than 0, it's 1. So we can just get rid of that. The lower limit's taken care of already, correct? This one stops our upper limit at t, provided what? Provided what? Nobody knows? Provided t is greater than 0. If t is less than 0, we have this. We have that. And then we're taking the integral from 0 to some negative quantity. That's not what we have. So for that reason, we make sure this is only true when t is greater than 0. When t is greater than 0, we'll multiply by 1. Otherwise, when t is less than 0, we'll multiply by 0. So that forces t to be greater than 0. Otherwise, we get 0 for an answer. Okay, now it's easy. Now we're on easy street. Integral 0 to t, e to the minus tau, e to the minus 2t, e to the positive tau, wow, d tau, all of that times u of t. Talk to me about this, e to the minus 2t. What about e to the minus 2t with regard to the integral?
Can it come out?
Come right out. There it is. It has nothing to do with tau. It's not a function of tau. Integral 0 to t. And now, either the minus tau times either the tau is 1 d tau. All of this is still multiplied by u of t. I don't want to throw away my u of t. What's the integral of 1? We're so sluggish today. Tau, evaluated from 0 to t, all times u of t, equals e to the minus 2t. And this is tau evaluated from where to where? From t, 0. 0. I plug in 0, right? Did we do all of that correctly? I made a mistake here. I think I dropped this. My fault here. Right here, e to the minus 2 multiplies there. There's 2. So this, I apologize. Darn it. This is not 1 inside of here. It's e to the minus tau times e to the 2 tau. So what does that give me?
E to the tau.
Yeah. And what's the integral of e to the tau? That's an easy one. Probably the easiest one. Okay, now let's evaluate this properly. So that's going to be e to the t minus e to the 0. E to the 0 is 1. Okay, let's just multiply it through. Equals e to the minus 2t times e to the t, e to the minus t, e to the minus 2t times minus 1 minus e to the minus 2t. U of t, u of t. Okay, let's get this answer in a faster manner. Okay, instead of doing this convolution integral, let's go here. Let's look at VI. VI is e to the minus t dt, or I'm sorry, not e to the minus t dt. VI here, e to the minus t u of t. Let's do that on this side. Okay, so VI equals e to the minus t u of t. And then we had h of t, just I've dropped the t notation here, don't have to carry it along with this, is equal to e to the minus 2t u of t. Great. VI equals, capital VI, VI of s. What's VI of s equal to? 1 over s plus 1. H, 1 over s plus 2. Now what?
Multiply them.
Yep, multiply those exactly. H of s times VI of s. So that's equal to 1 over s plus 1 times 1 over s plus 2 equals 1 over s plus 1, s plus 2. Now I'm just going to do partial fraction expansion so I can find the time domain answer. S plus 1, e over s plus 2, a equals s plus 1 times VO, not h, times VO of s, evaluated when s equals minus 1, and that's going to be equal to 1 over s plus 2, evaluated when s equals minus 1. That's equal to 1. And then b, we have b is equal to s plus 2 divided by, times VO of s, evaluated when s equals minus 2, equals 1 over s plus 1. When s equals minus 2, that's equal to minus 1. Great. Let's do the inverses. So that means VO of t equals a, 1, e to the minus t, plus b minus 1, minus e to the minus 2t. And then, if we're sticking in our u of t's, there's our u of t. Check. Awesome, unbelievable, very nice. So the same exact result. When we come back from break, what we're gonna do is we're gonna look at, so generally convolution is done one of two ways. One is I do the integral in the time domain. Two, I convert to the frequency domain, then do the inverse Laplace, get the time domain answer. The second one is more popular. However, there are functions that are small piecewise functions that are much, much more difficult to compute the convolution if you do the convolution using either the integral or if you do it utilizing the frequency domain. In fact, we will use the integral, but we're going to do it piecewise, piece by piece, and we'll see that when we come back. So let's go ahead and take a 5-minute break. Let's come back and we'll take a look at a convolution integral of two functions that are finite duration functions, and we'll see how that works. Okay, we're back. Before I do an example of a graphical convolution, I want to just step aside for a moment, and I want to show you that even though you don't think so, I think many of you actually have seen convolution in one way, shape, or form. You just might not necessarily recognize it. And the one place that I think you've seen it is in multiplication of polynomials. So I'm just going to make up some polynomials. I'm just making them up. S to the third plus 2s squared minus s plus 3. So let's call this polynomial number 1. So P1 of s equals this. And then polynomial number 2 will be, I'll do this. I'll make it longer than that one. So let's go s to the 5th plus 4 s to the 4th plus s to the 3rd minus s squared minus 2s plus 1. This is what I want you to consider. Consider here just the coefficients. So I want you to see the coefficients like this. 1, 2, minus 1, 3. Note that there are no missing terms. There are no missing terms. So I have s cubed, s squared, s to the first power, s to the 0 power. And for this one, the coefficients of this one are 1, 4, 1, minus 1, minus 2, and 1. So here's what we want to do. We want to multiply these two polynomials together. And I know that you know how to do that, and you've got plenty of ways to do that. But I claim that multiplying these polynomials is nothing more than doing convolution. I'm going to show you how I mean that. So first of all, I think we can all see that we're going to get an answer that looks like the following. There's going to be an s to the 8th power, an s to the 7th power, an s to the 6th power, an s to the 5th power, an s to the 4th power, an s to the 3rd, an s to the 2nd, an s, and then a constant. We don't know what those values are in between. I think every one of us can see that this coefficient is going to be 1. Watch how this works. So what I'm going to do is I'm going to take this right here and I'm going to flip it. So when I flip it, I get 1 minus 2 minus 1, 1, 4, 1. So when I flip it, I get that. Everybody see that flip? So this one here is that one over there, like that. Okay, so if we could look at this whole thing now, right here, if we could look at that whole piece, and I'm going to try to, this thing slides every time I don't want it to, so let's see if I can get it to slide. Yeah, I don't want that. Bummer. Let's clean this up. So we have 1, minus 2, minus 1. This whole thing slid on me. That was crazy. So now if you take that and you start sliding this in this direction, this is what happens. When we're looking at the overlap, let me slide this over a little bit. When we're looking at the overlap, I'm going to have 1, 4, 1, -1, -2, and 1. So it starts by overlapping. 1 times 1 is 1. That's the first one. Now slide it. So take this whole grouping and slide it. Slide it over by 1 unit. 1, 4, 1, et cetera, et cetera, et cetera. 2 times 1 is 2, plus 1 times 4 is 4. 4 plus 2 is 6, plus 6s to the 7th power. Slide it again. Okay, that was going to look like 1, 4, 1, and then you won't see the rest of them, so I won't bother with the rest of them. Okay, but they're out here. So -1 plus 8, that's 7, plus 1 is 8. 8s to the 6th power. Slide again. So when we slide again, we get rid of all of this, and we have 1 here. My eraser's not working. My eraser has faded away. There we go. 4, 1, -1, and of course out here is -2 and 1 still. So then I have 3, -4, that's -1, plus 2, that's +1. -1 is 0, plus 0, s to the 5th power, et cetera, till this whole thing slides through. And then eventually the last one is obviously going to be when this 3 by itself lines up with this 1. 3 times 1, that's going to be the last value. And so that last number is going to be 3 times 1, which is going to be 3 right there. So you've seen convolution, you just didn't know you were doing convolution before, but it's existed and it's been around you for quite some time. So convolution is nothing more than multiplying polynomials together and looking at the values that you get with the overlaps and then adding the overlaps together. Remember, the integral, the convolution integral, is a summation. It's the sum that we're taking. So we've seen this process before. All right, now let's do one of these convolutions that is a piecewise convolution. So in this example, we're going to compute the convolution through graphical analysis. Compute V O of t, which is equal to VI of t convolved with H of t for the following functions of VI of t and H of t. Okay, so graphical convolution means somebody's going to give them to you in a picture. So I'm going to try to be as neat as I can here with my graphing. So this is t. Let's use 1, 2, 3. Let's do it that way. 1, 2, 3. So this is going to be VI of t. This will be 2. And so it's going to look like the following. Okay, that's that function. So that's VI. Now let's draw what H of t looks like. One, 2, 3, 4. In this case, not a lot going on between these two. Let me get a ruler on this thing so I can draw this nicely. I want to go there. Roughly there. So let's let this one be blue. So it's going to be here to about there. Right. 0 there, 0 there. This value here will be 4. So this will be H of t. So I have two functions that are piecewise functions in their finite duration. And so we want to do a graphical convolution, and the way we're going to do it is by utilizing the definition of the convolution integral. So we know v out of t equals vi of t convolved with h of t, and that's going to either be equal to the integral 0 to infinity of vi of tau, h of t minus tau, or it's going to be equal to the integral from 0 to infinity of h of tau, vi of t minus tau, d tau. So when I'm looking at this, I look at the functions and I try to figure out which one is easier to flip. Which one is easier to flip? That's what I look at. Keeping in mind that often, unless we have something really easy like this one right here, often we have to write equations for the piecewise functions that we have. For example, does everybody see in this region right here, from 0 to 4, that this function is h of t in this region is equal to t. So we have to be able to write the equations for those functions. Okay, so here's what I'm going to do. I believe it is easier to flip and then shift vi, because vi is a real easy function. It's not that h of t would be much more difficult. So what I'm going to do is I'm going to start first by showing vi of minus tau. So just the general vi of minus tau. And that looks like the following. Minus 1, minus 2, minus 3. So I just flipped it about the tau axis. This is now tau. That's the tau axis. And this height, actually, I drew it too high. I should probably pull that back down to make it look like the other one. Even though I can put any scale I want to on my axis. Okay, 2. So that's vi of minus tau. And then vi of t minus tau is going to be shifted t units either to the left or the right. If t is negative, it's shifted to the left. If t is positive, it's shifted to the right. Just to be sure that we are in the know, this function here is that right there. Actually, let's draw it in blue so it stands out a little bit better. So that is h of tau. So somebody tell me, how hard is it to turn h of t into h of tau? How hard is that?
Replace the axis.
That's
Fatal
it.
T.
That's it. Just change the letter t on the axis to a tau, and it's done. Okay, now what we're going to do is, now we have to look at what happens. So clearly right now, I have not shifted, in this picture, I have not shifted vi of minus tau. So right now, what is the value of a little t? In other words, in this, vi of t minus tau. Right now, for this picture, what is the value of t? Everybody agree it's 0? T is 0. When I plug in 0 right there, I get, I get vi of minus tau. Yeah, that's what we have right there, vi of minus tau. Okay, now we have to use our brains. So there are different regions where different things happen. And generally what you should do is you have to establish the region, show a picture of those regions so you can see exactly what's going on, and then compute what the integral is in that region. So here we go. There are multiple regions here. I'm going to start number one. This is going to be t is less than or equal to 1. And the reason I'm using t is less than or equal to 1, and putting words here, we're going to find out that there's no overlap of these two functions. We'll see what I mean by no overlap in 2 seconds. So I'm going to draw a typical picture in this region. All right, so each of these pictures we're drawing is a typical picture of each region. So what does that typical picture look like? Well, if t is less than or equal to 1, this guy has not reached the axis yet. When t is equal to 1, it will slide all the way over, it'll reach the axis. If t is less than or equal to 1, it's somewhere over here. So here's a typical picture. This function is somewhere over here. This leading edge is t minus 1. This trailing edge is t minus 3. Notice all I did is add a t to that. That's how you figure those out. Just add a t to it. This function over here is still this. Now remember what the integral is. The integral is, so I'm going to write it down here so you can see it. So right now in this region, right now, vi of t is equal to the integral from 0 to infinity of, which one did we use? We used the h of t. Vi of t minus tau, is that the one that I used? Which one did I flip? Which one did I say the first one was? Yes, Vi of t minus tau. Good. Okay. Vi of t minus tau, keep it there. D tau. The product. What happens when I multiply those two functions together? Here, let's start here in green. What's the value of the blue one right over here? For this value of t, what's the value of the blue function?
The 0.
What's the value of the red function?
Zero.
Good. So there's no overlap. These functions, the pieces here do not overlap each other. So you're going to get 0 multiplied by 0 everywhere else. So this is clearly equal to 0. So for any t less than or equal to 1, Vi of t is equal to 0. That's what we're saying. Vi of t equals 0 for all t less than or equal to 0. I'm sorry, less than or equal to 1. Okay, that region's done. Now you can see as this continues to slide in this direction, at some point in time, it's going to cross over the axis and there's going to be an overlap. And so the next region that we want to look at is what I call partial overlap. We'll call that number 2 now. And that partial overlap, so in this region, it's going to be 1 is less than or equal to t, less than or equal to 3. You'll see why it's 3 in a moment. And this is where we get partial overlap. So let's draw a typical picture. The beauty in this typical picture is that blue function, it doesn't move. It stays the same all the time. The only one that's sliding is the red one. So our tau axis, the blue one, 1, 2, 3, 4. Blue still looks like this. 0 everywhere else. And then the red one now looks like the following. Because we're restricted to t is between 1 and 3, I have a partial overlap. Some of it's here, some of it's over on this side over here. The rest is 0. The rest is 0. So 0 times anything is 0. 0 out here. Blue is 0. All of that. And we're integrating from 0 anyway. So now here's what we have. Keep in mind that this function has a value of 2 here. And this function, we said h of t in this region was equal to t. So h of tau in this region is equal to tau. So what I have is the following. I have the output, u of t, is equal to the integral from where to where? Well, what's this leading edge right here? This leading edge is going to be t minus 1. And the trailing edge here is always t minus 3. It always stays the same. All we're doing is we're looking at different regions of t. So can you see how this integral, we're only going to get values, nothing there. We're not going to get any values there. It's only going to be from 0 to t minus 1. That's the only place that we have the overlap of the two functions, and when they multiply each other, we don't get 0. So what are the functions? Well, the one in red is equal to 2. The one in blue is equal to what? What's the one in blue equal to?
Tau.
Excellent. Wow. Who said that? Who got that?
Jordan.
Jordan, was that you?
Yep.
Outstanding. The function is tau in that region. So I multiply those two together and I integrate away over the time. All right, well, we all know how to do that. So there's 2 tau integrated. Fortunately, these are easy functions to integrate. So 2 tau integrated is 2 tau squared over 2, evaluated from 0 to t minus 1. The 2's cancel. This is equal to t minus 1 squared minus 0 squared equals t minus 1 squared. Let's leave it just like that. T minus 1 squared is beautiful. So in this region, let's do them in green. I did them in green before. The first one. So in this region, we know that V out of t is equal to t minus 1 squared. That is for 1 less than or equal to t less than or equal to 3. I want to check the border. I want to check the border with you. So notice that this one here is valid right here for t is equal to 1. This one up here is valid for t is equal to 1. What is the value of vi of 1 up here? Vi of 1, what's it equal to? According to this equation that we're looking at here. What's it equal to?
0.
Good. That better match up with this one down here. So let's check this one down here. When t is equal to 1, vi of 1 equals 1 minus 1, 0, squared, 0. Beautiful, check. So the boundary's checked. That's a very nice, quick check to make sure that you may not have made a mistake there. So that's our second region. So the third region is what I call full overlap. And that's going to happen for 3 less than or equal to t less than or equal to 5. That's going to be full overlap. Draw a typical picture. And what has happened here is one, oops, not that one. 2, 3, 4. So we have that function there. That's what the blue one looks like. This is what the red one looks like. The red is somewhere like this. And it fully overlaps the blue function. For the part where it's non-zero, it fully overlaps. Its value is still 2. That value is still tau. And so now what we have here is we have the following. So we have V of t equals integral. Where can I do this integral from now? Well, don't forget this leading edge is always t minus 1 and the trailing edge is always t minus 3. So I'm going to get 0 there, 0 when I multiply there. So I'm going to integrate from t minus 3 to t minus 1. That's where I have the overlap of the functions. That's where I have non-zero values. And so it's going to be 2 times tau. Notice it's the same thing every single time in the integral. That's awesome. D tau. So again, this is going to be 2 tau squared over 2, cancel, evaluated between t minus 3 and t minus 1. Let's put those values in there. So that's t minus 1 squared minus t minus 3 squared equals t squared minus 2t plus 1 minus t squared minus 6t plus 9 equals 2t negative minus a minus 6t, positive 4t, and then a plus 1 minus 9. It's going to be minus 8. I'll just write this a little bit easier. It's 4 times t minus 2. Okay, let's check the border again. So let's write this down in green first. So this is what we have. Vi of t equals 4 times t minus 2. And this is for 3 less than or equal to t less than or equal to 5. Let's check the border. Check on 3 here. So when t is 3, 3 minus 2 is 1, and I get 4. So v of 3 as a check equals 4. Let's go up above in the previous one. When t is 3, v of 3 equals 3 minus 1, 2. 2 squared equals 4. Check. Awesome. So those borders always should align. Always should align. There's your double checking. Okay, we have 2 more regions. The last one is the easiest. The next one is, I want to say it's difficult. It's the inverse of that, the second one that we had. So we're going to go back to partial overlap again. So this region would be our region number 4, and that's going to be, that partial overlap is going to occur from 5. You can see it's always in increments of 2 seconds, right? It's going to be from 5 to 7. So it's going to be 5 less than or equal to t less than or equal to 7. And this is where we have partial overlap again. Typical picture. Always draw a typical picture. Easy to see, easy to understand. 1, 2, 3, 4. Scroll a little bit further. Our blue function. Keep in mind that that's 4. Our red function. Our red function now looks something like this. Okay, you can see from the red function, it's 0 here, 0 here. The blue function is 0 here. Let me put that in there in blue. The blue function is 0 there and all the way out there. They're both 0 out here. So clearly the only overlap is from here to here. This is the trailing edge this time. We've been following the leading edge is t minus 1. The trailing edge is t minus 3. So this time, v out of t is equal to the integral from t minus 3 to 4 of 2 times times tau, d tau, and this is equal to twice tau squared over 2, cancel, evaluated from t minus 3 up to 4. Now all we do is just substitute in these final values here. So that's going to be equal to 4 squared minus t minus 3 squared equals 16 minus t squared minus 6t plus 9 equals minus t squared minus plus 6t, and then 16 minus 9. 16 minus 9 plus 7. Okay, not bad. Not difficult at all. So in green, again, we'll just write it in green. So what we're saying is VO of t equals minus t squared plus 6t plus 7. And in this region, this was the region minus 5 less than or equal to t less than or equal to 7. Should we check 5 to see if, not minus 5, positive 5. Should we check 5? V0 of 5. So what happens when we have 5? We double check that one. It should match our border from the previous one. So when we plug in 5, this is equal to minus 5 squared plus 30 plus 7. So 37 minus 25 is 12. Let's check the previous one to see if that matches. For 5, 5. 5 minus 2 is 3. 3 times 4 equals 12. I have a lot of confidence that my equations are correct. Nothing guaranteed that they're correct, but I have a lot of confidence that my equations are correct. Okay, so there's one last region, and the last region is, I think, is pretty obvious. That last region is when there's no overlap, and that's going to be when t is greater than or equal to 7. So I think that's region number 5. T is greater than or equal to 7. Back to no overlap. No overlap. Typical picture, which quite frankly, you probably don't even need to draw. 1, 2, 3, 4. So we had this function here. That's the blue function, like that. And then the red function is somewhere out here. The red function is somewhere out here. So you can see how there's no overlap on that red function at all. So clearly, VO of t equals 0. I'm not even gonna write the integral because there's no overlap. So when you multiply those two functions together, you get 0 for all tau. You get 0 for all tau. So this is for t greater than or equal to 7. So typically what's done is the following. You take all of those sections, you put them all together, and you write them as one function. So like the following. VO of t equals, bloop, bloop, and we write all these regions. 0 for t less than or equal to 1, and then it was t minus 1 squared, or 1 less than or equal to t less than or equal to 3, and then it was 4 times t minus 2, not squared, sorry, no square there. Get rid of that square. And that was from 3 to 5. And then it was minus t squared plus 6t plus 7. 5 less than or equal to t less than or equal to 7. And then finally 0 for t greater than or equal to 7. So that's how we write it. So we would box that up if we were asked for that. Often you're asked to plot that function. So let's graph, or let's plot it, sketch it. Sketch is a better word to use. Let's sketch that function so we can see what that function looks like. Let's pull it down so we can see what those values are. So 1, 2, 3, 4, 5, 6, 7. This is on the t-axis now. So it starts off at 0 all the way up to 1. Then it's t minus 1 squared, and we know right there at t is equal to 1, we know it's 0. Then when t is equal to 3, 3 minus 2 is 4. So we're going to be at 4. Let's call that 4. When we're at 3, we're here. And it's behaving like a squared function. That means it's going to look like this. That's what a squared function looks like. Okay? Then we're in 4 times t minus 2. It's behaving linearly from 3 to 5. And when we get to 5, 5 to 3, 12. So we're up to 12, 4, 8, 12. When we get to 5, we get to there, and we're doing it in a straight line. I'm going to draw the best straight line. There it is. Then it's a squared function on the way back down. This is going to be concave down. If you know your concavities of functions, it's going to be concave down. And by the time we get to 7, it's going to be 0. We didn't check this, but check it. You'll see that by the time you get to 7, you get to 0. So it's going to be a concave down function. I can put in a test number to see how much of a concavity I have, but it's going to come down like this sort of thing. And then flatten off like that. That's the function. That's what it looks like. I would ask you this question to ponder. Have you seen anything like this kind of a function that we're staring at right now that we've taken the Laplace transform of? Or that we know it's Laplace transform? Do we know it's Laplace transform? Yay or nay? Do we know it's Laplace transform? I think the answer is no. If any of you knows the Laplace transform, come talk to me. I want to get you into grad school immediately. We don't know that Laplace transform. It's a piecewise function. That would be an ugly, ugly mess. It can be done, but it would be an ugly mess because there would be a lot of e to the minus 3s's in there, and e to the minus 5s, e to the minus 7s, e to the minus s. There'd be a lot of those terms that are in there. So this function is a pretty ugly function. It's not a real clean function. All right, let's pause on that for a moment. Any questions that you have about what we've just done with regard to the convolution integral? I want to specifically know if you have a question on what you did or what we just did here. How many of you could do that again? How many of you could do that on your own? If you had 2 fairly simple functions to go through those steps. Basically what you're looking for is as I slide this function through, and that's all we did, we just slid it through that little pulse function. As we slide it through, we're looking for what are the different regions where new things are going to happen. That's what you're looking for. So for example, if we had the following. If I had one function kind of like this, your book does a couple of them that look like this, and I had another function that looked like this. Notice as this is sliding through, different things are going to happen when it gets to this point. Because here, yeah, that might, I'm just making it up. Maybe this is 2 tau, that's that function. But this function over here is, looks like it might be negative 2 tau plus 20, for example. So once this crosses over this line, then we've got part of it is multiplying from here to here. It's multiplying this function. The part of it that's in this region is multiplying this function. And now you've got to break that integral down into a number of different regions. And so that can get a little bit uglier. And I'm not claiming that I want you to know how to do that, but there are homework problems in the book where they look at exactly these kinds of things. The easiest ones are these. That's pretty easy. Oh, that just slides over. These are easy. They're just constants. That's a constant value. They're not even functions. I will tell you, when you take a function like this one up here, and you want to flip that one, God bless you doing that. So this 2 tau needs to change into a t minus tau. That's not really cool. This one here needs to turn into a t minus tau, and this gets really ugly. Always flip the easiest function to flip. Always flip the easiest one. It's the best way to go. All right, I'm going to leave it at that for today. We'll call it quits about 5 minutes early. You get an extra 5 minutes start on your weekend, unless we have any questions before we part ways. I have homework problems for this chapter. Do you want homework problems right now that I can give you that you can look at? I got a couple of homework assignments. I didn't see all of them, but I saw 2 of them come in. Why don't I do that? Why don't I give you these for those of you who want to start looking at some of these problems? Because you can definitely look at these problems. And what I'm going to do is I'm going to reserve Monday. We'll probably spend about half the lecture working on problems. And then Tuesday, we'll spend more time just looking at problems so that you have problems that you can look at. So this is chapter 13. And that is on page 522. It's amazing. Page 522. 4, 9, 19A, 27, A and D, 30, A and C, 51, 54, 55, 63B. 63B is a fairly easy convolution if you want to check your understanding. Pretty easy. And then 79. I believe you have the tools to be able to do every problem right now. I believe you have the tools to be able to do every problem. So you can go ahead and get a head start on that. Questions?
Are we going to do the final just how we've done the quizzes?
Say that again, Jack.
Is the final exam the same format as the quizzes?
It'll be, yeah. My expectation on that exam is there's probably going to be between 8 and 10 problems, and it'll be just like a quiz problem. Just like a quiz problem.
Okay. I just mean how we're going to do it. Is it going to be?
Oh, yeah. Well, yeah, except it'll be a longer period of time, right? Then you'll have to scan in all of those sheets. I will send that to you. Is there anybody who doesn't have a computer available to them that they can't print those sheets out? Because it'll be easier if you have access to work from those sheets. I think it'll be easier to have access rather than writing them down and doing your own thing. It might be easier to write them. But yes, the format will be the same, Jack. Okay, in fact, we'll probably have a quiz on Monday, hint, hint. Okay, if there are no other questions, have a great weekend, have a safe weekend, stay away from people, be careful, and don't hesitate to reach out to me if you have any questions on any of this material that you don't understand. Take care, look forward to seeing you next week.